Okie dokie, it is 7:30 and we're going to get started. Now it's 7:30 and 15 seconds and we're going to get started. No, you're not. Okay, I'm getting ready to get it out. Dr. Masood. Come on, you guys. All right, welcome to the July meeting of the Johnson Space Center Astronomical Society. Oh, well, that's one of my pictures. Anyway, I was going to say that our picture brought to you by somebody, but that's one of mine. So there it is. That's the Lagoon Nebula and the Trifid Nebula right next to it. Milky Way. That's what it actually looks like. Okay, before we get started here, well, here's our agenda for this evening. And we'd like to welcome anyone who this is your first time here. If it's your first time, raise your hand, tell us your name, how you found out about us, and what your interest is in astronomy. Anybody first time here is willing to admit your first time here?
It's actually the second time you know, like again, but we didn't have to actually introduce ourselves. So I let David start. Observatory in May. Unfortunately, the weather wasn't helpful, but we love it.
Great.
Welcome.
Yeah, welcome. We're glad you guys are here. All right. Anyone else first time here? Willing to admit it's first time here? No one else. Good enough. All righty. We have a email distribution. If you'd like to get on our email distribution, send an email most likely to David at the bottom, starhopper457@gmail.com. If you can't get that written down quickly, there's little tear off tabs up there by where Al is. Hey, Al, you want to hold up the tear off tabs? There you go. Tear off one of those and you can send David an email and get on our email distribution. Okay, speakers. If you're a speaker tonight, please use this mouse pointer here so that people online can see what you're pointing at. The stream mic is in the computer. The auditorium mic is in the podium. So I'm sorry to say you can't go wandering all over the place because the people online can't hear you. So you need to kind of stay kind of in this general area so everybody can hear what you have to say. All right. So our main speaker tonight is Rodney Rocha. And I think a lot of you guys know Rodney. He's been around here, I think, actually longer than I have. And before Rodney comes up here, let me tell you just a little bit about him. I'm going to see if I can do this without my glasses. Okay, Rodney Rocha is a recent retired NASA aerospace engineer. He's served 5 decades at the Lyndon B. Johnson Space Center. His expertise is in Newtonian dynamics, vehicle and structural dynamics, and structural vibration testing. He supported the early space shuttle studies and testing, space station designs, and many other projects, such as engineering support to the new lunar exploration spacesuits and the current human lunar exploration programs of Artemis, Orion, Gateway. His hobbies include mathematics and orbital mechanics. He is a current member of the JSC Astronomical Society and a founding and current member of the Corpus Christi Astronomical Society. And let's welcome Rodney.
Thank you, Doug. I will be referring to some notes down then. Let's see if I can get this started. So
Enjoy.
yes, thank you. And I'm going to be interactive with you, the Socratic methods, because I'm interested in what people's intuition are, or how they conjecture stuff, even if you haven't gotten very deep into physics or mathematics or astronomy. I'd still like to know. And as a courtesy to those that are still learning these things, and you know the exact answer, let's try to let the audience members use their answers. And there's no wrong answers. There's only imagination and innovation. Yes, physics has the correct answers, but the way you get to some of the physics laws, people were conjecturing and wondering about things. Sometimes they were right, sometimes they were dead wrong. Okay. Enter. Okay, my slide is up there, and I hope everybody online is able to see the cover slide. I won't do the voice impression, but this is a paraphrasing from a very well-known genre, okay? An energy field that surrounds and binds all living and non-living things. You feel it around you, here, between you and me, the trees, rocks, this building, everywhere. Yes. So who might that be? Let me see. Enter. Okay. We can conjecture on that. So who's got a guess on who I was talking about or where that might come from? Oh, we don't have we need some younger people, I guess, from 1977. The Force. Your dog. Aren't you? The Force, an ally it is. Okay. All right. So we have to be grateful sometimes to biology and microbes that caused the Great Plague of London in 1665, because there was a young student there at Oxford or Cambridge, and he was told, and all the students, go home. There's a plague and people are dying. They're dropping like flies. So that was a very fruitful period for him to go home, because he could now let his mind freely think and solve problems and things he was pondering about in mathematics, physics, optics, and many other things. And we think that, it's apocryphal that he was seeing apples fall. And of course, he wanted to solve the exact formulation for the law of gravity. Well, he wasn't the only one. Scientists they didn't call themselves scientists in those days. They called themselves natural philosophers. They were interested in everything, including languages, history, and all sciences. And they had their favorites, of course, but they were natural philosophers. Well, the natural philosophers and mathematicians of Europe, continental Europe, everybody thought it was, they'd accepted the Copernican theory and the sun was the center of the solar system. But what's this attractive force? It's like a magnet, but it's not exactly like a magnet. We know how magnets work with metals and ferromagnetic materials, but it's attractive. It pulls things. Yeah, we know that. Everybody knows that. But what's the formula? Plus, whatever it is, we can't explain comets. They're taking paths that are not like the planets, these strange hyperbolic and parabolic paths. What kind of law, what kind of force is that? Or are they coming in with, well, we don't know. They're just coming in, and the sun, one idea is the sun's pushing them away with a solar wind. Sun just blows them back. That's why when they disappear to the bright sunlight, you can't use a telescope anymore, at least in the 1600s. You can't look anymore, you're going to get blinded. The comets seem to go into the glare and then they go away. The sun hurls them back. That's what it is. It's a fluid. It's a fluid that pushes. Hey, I can't rule that out. Well, no. Okay. More was to come. We needed a formulation. Plus, that was hard to explain. Now, I'm not going to say what causes gravity. I don't know what it is. I just know that there's two ideas. There's two two branches of physics, that the Newtonian physics that says it's an attractive force and has a very precise formula, that gravity equation down at the bottom, inverse square law. And then later in the 20th century would come the other gentleman, Einstein. And Einstein just say, forgive me, Newton, but this is my upgrade to it, and so on. However, there is a bridge between the two. This is just my thinking here. I'm not saying I know fact here. Even though Newton, let me see if I can get this. Here's G, that's a constant. That's empirically known. You don't derive it with physics. You got to measure that in the lab by somehow. So you have to measure these masses, two masses that are attracting each other, and R is a distance between them, and it's squared and it's over there. But G is the strength of this equation. But if you notice, let me see. There's Einstein. Now he appears, and that's his tensor equation that says relates curvature and strength and stress of the universe in a simple. But those are tensors. You can that's not just an algebra equation. It's a deeper layer than even vectors are. Vectors and matrices, but tensors go beyond that into more dimensions, more derivatives. And Einstein had to learn that himself through Minkowski. I think I read somewhere he spent maybe a year with Minkowski, his friend, to learn tensors and how to really do it right, But G appears there and it appears here. That's the same constant. So on the one hand, Newton is saying it's a force, an attractive force, radially directed inward. And Einstein says, well, it's not really a force. It's mass. The presence of mass and distribution of mass in the universe distorts space. Free masses moving around follow the world lines. The world lines there's no other forces on them except the curvature of space causing them to move around and whirl around planets and get deflected. And he said, I'm not talking about forces like impacts or rocket thrust or collisions, not that stuff. I'm talking about a free particle, free mass moving serenely through the universe. It encounters the distortions of space-time. So, but the bridge between the two is G, that big G. They still have to use that gravitational constant. It's empirically measured. It's not derived. So, all right. So let me see, enter, not arrow. Well, the yellow text that just appeared just said a little more elaboration of the Einstein tensor. I think I'm not going to read it for you. All right. In the 1600s, there was a publication called Mysterium Cosmographicum by Johannes Kepler. He, like all the others of his time, had accepted the Copernican theory. The sun is the center of the solar system. The 5 known planets are whirling around the sun in paths, but they don't have telescopes. So what he wanted to do is take the data. There was exquisite reams and reams of paper by the Danish astronomer Tycho Brahe from Denmark. And he measured the position in the sky with these instruments, but there were not telescopes. They didn't have lenses and telescopes, but they had these long beams that were calibrated, and they were specially constructed so they wouldn't sag. He wanted as close to perfect, a straight line beam that he could move around, record angles and the precise time. And that's all he did. He just books and books and books of this stuff. Well, Copernicus wanted to go through it and derive something. He said, well, how are these planets moving? What paths? Can I get laws out of this? Well, he was a scientist, but he also let his bias and prejudice get to him, because he thought, like many others, if there's a divine order to things, it'll be related to geometry and beautiful things like these nested objects that's shown on the right-hand side, kind of like the Russian nested dolls, they keep going in. There's 5 of them, and maybe there's a 6th one according for the sun. The sun needs to have one, and it's in the center. So they have to be nested, and you can see their names: octahedron, icosahedron, dodoberdahedron, all those. And he said, it's got to be something like this. That's the spacing of the planets. There's got to be divine order. So it's mathematics that's symbolic, related to geometry, because geometry is beautiful. Geometry is solids and shapes and stuff. There's no math in there. It's visual. So the divine creator had to do it. Well, he poured through the data. It's not working. Not working, not where I'm forcing it. I want to force it into my idea. So what he did was abandon the thinking like a true scientist is supposed to do. What do the data say? What do the data say? What emerges out of the data? Let the universe talk. So he did that. Let me see. Okay, enter. Okay. Here's the conic section. This is a preface to what I'm going to get to. I think I talked about this in 2019, but I think most of you have seen it. If you take a right circular cone, in this case, let's take 2 of them with their points. One's inverted, and their points are touching each other. I'm going to explain why I'm doing that later. But if you take a cutting plane, that blue plane there, let it slice very, very sharp. So slice it parallel to one side of the cone. And what is a right circular cone? Well, it means the base is circular, perfect. And right means that the upright, the center line of the cone, it's not tilted or slanted. It's perpendicular to the base. That's a right circular cone. But if you take a slice, say parallel to one side, you get a parabola. I maybe should have started with the circle first, right here. Slice it like this, that's perpendicular to that upright vertical line. Anywhere you cut it, anywhere you cut that cone, like that, you get a circle. Well, their circles are going to be different sizes. And if you move the plane up to the points where they're touched, well, it's going to be a point. It's like the circles are collapsing to a point. Now, if you tilt the cutting surface again, but not like this, this is parallel to the side, but don't go that far. Just cut it, but not to the point where it's parallel to a side. You get these ellipses. One's an ellipse, ellipses plural. You get various ones, and they get their different amounts of squishiness. Well, what about if I tilt that cutting plane? Those online can't see me, but I'm just tilting it, not quite to the point of the circle, but they're approaching a circle. You'll see that if I'm cutting it, but I keep getting that cutting plane horizontal, I'm approaching a circle. So a circle is it's a form of an ellipse. So when I tilt it, what happens to the circle? It gets squished. It gets ovalized, or in mathematics, it's eccentric. It's deviating from a circle. And that measure, you're going to see it later, a little value called eccentricity. So that means it's the measure of how much it departs from a circle, how much squishiness it has. Then you have something really interesting. So far, those upper cones in the first 3 examples haven't participated. Like those cones are just sitting there. Well, you haven't cut me yet. But if I make the plane vertical, where it cuts both of them, I get a hyperbola on the bottom and a hyperbola on the top, hyperbole, plural. And you think, I'll illustrate with another figure here. Here's their names right here with the different angles of cutting, how you cut them. Well, the ellipse is going to be of interest to us because that's what Kepler was going to discover. He was going to discover that's the geometric shape that seems to explain planetary. It's what the planets do. It doesn't explain what comets do, but it seems to explain planets. Now, the hyperbola, well, on the upper right figure, I see one, but you see with the cones, when you have 2 cones tip to tip, one's inverted, I get 2 of them. Is this why 2 hyperbole? is there physical meaning to this? Sometimes, like when you solve a quadratic equation, it's like x squared plus x plus a number equals 0, or you may have coefficients in there. You get two solutions. If we use the quadratic, it comes up in dynamics, like in my field, you run one object into another, or it could be docking, or if an astronaut falling down and hitting the floor or grabbing a handhold. If you model that with what we call linear structural dynamics and linear springs, you get two solutions. You go, well, I thought I only got one impact. How come I got two solutions? There is physical meaning to two solutions. You don't, sometimes the second one doesn't have any physical meaning. You throw it out because it's like, well, that can't really happen here. But why do you get two? You get two hyperbolae here. So we know now in advance, comets that are coming in that we think were born in the solar system, maybe the Oort cloud or the Kuiper belt, when they come in and they're falling and they've been disturbed, the planetary motions have disturbed, pulled one in, and centuries, millennia ago, they started falling in. They tend to take very highly eccentric ellipses. But if it's coming from interstellar space, and you remember, what was that? Well, Muamua from years ago, and there's another one. They're being discovered, and our instruments are so good. We're seeing objects coming in from interstellar space. They're hyperbolas with strong eccentricity. The value, if they're born in the solar system, it's nearly 1, or an ellipse is 0.9999999, whatever. It's almost a parabola. But a parabola is exactly 1. But if it's got like 1.4, that's not the solar system. That's coming from way interstellar birth somewhere else. Something got it going, whatever. So that's a clue in the orbit that it's not from here. It's not one of us. It's from out there when it's a strong hyperbola. But why 2? Well, the hyperbola describes with gravity, the laws of Newton, the gravitational attraction, it takes that shape. That's a course in orbital mechanics. I wish I could put in more there. I was going to show you some more equations. I'm not going to. I can't. No time. But what's the other hyperbola for? Two charged particles, like 2 electrons or 2 protons. If you fire one at the other the correct way, they will repel each other. It's the path, it's a hyperbolic path of repulsion. It's how a charged particle repels another one. It doesn't swing around it like a comet going around the sun. It stops short of the other proton and goes away. It just does a hyperbola in front of it and deflects it. So that's the meaning. That's the physical meaning. It describes high-speed repulsion. Now, on the upper, oh no, that's the next slide. We're going to go back to the ellipses because I'll get to Kepler and a little more about him. What he discovered is ellipses are going to be very valuable for me. So this is just one generic ellipse. It's just a squash. You take a circle and squash it a little bit, but it's a highly regular. It's symmetric, and that's the center of the ellipse there where I have the marker. This line up there says 2A. That's the major axis. Its length is 2A. Why am I saying 2A? Why not just A? Because the formulas in orbital mechanics use the half values. They'll divide by 2. So this author, they'll often say, well, let's just say it's 2A. So half of it, we're going to call the semi-major axis. So that's going to be A. That's A. The minor axis is this one here. This is the vertical dimension here. I just drew it this way. You can orient it any way you want. It's 2B, so the semi-minor axis is B. E is the eccentricity that I talked about, how much squashiness. So let me see, I think I put this one I didn't want to pronounce because you might think I'm being vulgar. So it's the distance, this line through the focus. Every ellipse has a focus. One here, one here. The sun will occupy one if we're talking about the solar system. The other one is called the empty or vacant focus. But if we're talking about the solar system, the sun will be here, or a two-body problem where there's two masses, one's revolving about the other, it will, that'll be the focus. In reality, when you have two masses, they're really revolving about the common center of gravity, called the baryon. I think it's called a barycenter. But they're doing ellipses around that center. Both of them are doing ellipses around that point. And there may be no mass there at that focus. Like two stars, that often happens with stars. They approach and they swing around this empty point, their common focus, but there's nothing there. It's just a focus of an ellipse. So this vertical line here is called the lattice rectum, and it does appear in a lot of formulas too. Okay. So eccentricity is a big thing. That's the measure of the squishiness. Now, Kepler, that's where he born 1571, but he was doing his work in the 1600s, took all those books and reams of data without a telescope. Only 5 planets were known, which, you saw them named a while ago. I hope you can name them in your head, right? There's Vulcan, and then there's, no, I'm kidding. It's the non-telescopic planets that the ancients knew and shepherds knew for tens of thousands of years, and gave them mythological names and meanings and all that. One thing I read in some reference that without a telescope, if the planets all had circular orbits, if they were elliptical, but just slightly, it would have been hard to determine that they were moving in ellipses at all. What was lucky for Kepler is that Mars, let me see here, has an appreciable eccentricity of like 0.2, something like that. And Jupiter, or is it's Mercury. Mercury and Mars have these enough that they appear in the data as strong ellipses. But if you look at Venus, 0.007, the James Bond number, that's very small, very small. The Earth is very small. But he was lucky that Mars is fairly close. We make a close encounter. So he was able to see those motions pronounced, and it had enough eccentricity to give him data to make his conclusions. So his laws, I said right there, the eccentricity Mars 0.21, Mars at 0.1. Mercury's got the bigger one. Maybe he was lucky. If they'd been, the other ones are an order of magnitude less, like a tenth of that or less. It'd be very hard to discern anything out of that data. So his laws were the orbit of each planet is an ellipse. Sun's always at the focus for all planets. Ellipses have 2 foci, that plural of focus, but the sun is at one. What's at the other? Nothing. It's called the empty or vacant focus. So for each planet, the rate of area swept out by the radius vector, is constant, conservation of momentum. So the demonstration of that is, here's this. I've got a stick. I know people online can't see me. It's a yardstick, meter stick, but see these zones here? There's one, here's blah, blah, blah. Suppose I have little tiny paint brushes dangling from here. I'm going to dip this in paint. Now I'm going to make the solar system a table. So where my hands are, that's the sun. So if it were a circular orbit, I'm just doing this. So I'm sweeping out of here. I'm painting the table with paint. I dip it in paint. So I'm painting. If it's a circle and I'm at constant rate, I'm sweeping out area at a constant rate. But what about an ellipse? What I'm doing is, maybe I start out at the far end of the ellipse. Here's the sun where my fist is, but way out there's, now as I move away from there, that ellipse is coming in, it's ovalized. So maybe I'm in this zone. So only these these don't paint anymore. So I'm sweeping out some paint on the floor. And as I come closer to the sun, I'm getting closer and closer. All these paintbrushes are dissipating. I can only use the ones here where my finger's sliding. Well, it's moving faster and faster and faster. So it gets to sweep out more area, the same amount of area in the same amount of time. So the point is, it paints an area at a constant rate. So that's amazing that he was able to see that. I can't even figure out how you can get that from a bunch of numbers, but he did it. But from Newton's laws, well, let me say that in a minute. Let's go to the third law. For each planet and its elliptical orbit, the cube of the semi-major axis, that's that, the long part, the long dimension, take the semi-major axis, and it's proportional to the square of the period of revolution. What's the period of revolution? Got a stopwatch or my watch or grandfather clock, whatever. How much time does it take to make one complete revolution? That's a period. That's just called a period. So the cube, if you take that length, the semi-major axis, and just say half of it, cube it, just make it a cube, it's proportional to the period of revolution. From this and the other laws, you get that Keplerian motion. The closer you are to the sun, the faster the planet's going in its orbit. Like Mercury is the speedy one, right? The messenger of the gods. It's going 88 days in one rep. That's a period. Venus is more. Earth is, it's the basis of our year. What's that number? I'll use the Mayan calendar there. Anyway, it's 365 days and a fourth approximately, and on and on and on. And what's Pluto's? Well, Pluto, if it were still a planet, 200 years, none of us are even 1 year old yet in Pluto years. But from this, you get what they call Keplerian motion. The closer you are to the sun, the faster you go. The further away you are from the sun, the slower you go. And despite these eccentricities, if you drew these planetary orbits to scale, they'd look like circles, even if you put them on a large piece of paper, except Pluto. Maybe it's slightly squished and it's inclined to the rest of the planets. All right. Bridging Newton's and Einstein. I kind of already mentioned it's G, that gravitational constant appears in both. There it is, and there it is. And both are practically equivalent at low speeds and low enough mass density. Forgive me, Newton's what Einstein said. So where do they start breaking down that they don't agree with each other and Einstein is more correct? It's when you're in the presence of strong gravities, like you're near or at the surface of a neutron star or near a black hole, or relativistic speeds, large fractions of the speed of light. But we're not there yet. We're not. But nature hurls objects at near the speed of light, those relativistic jets of black holes. That's, to me, as a technological standard. When we can do that, we really accomplished technology. If we can hurl trillions of tons of matter near the speed of light, well, it happens all over the universe. There's those engines natural engines are doing that. All right. And that little drawing on the bottom right is in the lab, you get torsion masses. It's a torsion wire, and they measure the string, two masses, those gray masses here, their forces, their masses, and they're attracting these little ones on a little bar hanging by the string. So the amount of twist, they can measure that force, the torque in that wire. And it's hard to do. Out of all the physical constants, there's dozens and dozens of physics constants. This one has the least significant figures. It's so hard to measure. There are others, Planck's constant, all that. They've got like 10, 12, 15. Precision is real long. There's only like 7 or 8 in the Newton's constant. So what a lot of orbital mechanicians do is they use GM, like if the Earth is M1 or the sun, it's easier to measure GM. They said, well, what's M? Well, I don't need to know that. I'm doing orbital calculations and trajectories. All I need is GM. I don't need to know exactly what the mass is of the big guy. I just need GM, and that's much easier to measure. In fact, you can derive it from the trajectories you get. The little satellite or spacecraft, well, that is easy to measure. You just ask Boeing to give you no, wait, you ask another company to give you that. Okay. All right. Now, Kepler did something amazing. It's standard now in orbital mechanics. I drew you kind of know that elliptical motion, You get close to the sun, it's going kind of fast, whips around the sun. And once it whips around the sun's gravity is retarding it. So it's slowing down. So, right, let's see, the sun here is at the focus. So this planet goes around, it going, speeds up, reaches its maximum speed here. And you study orbital mechanics to get all this and all the formulas. Then it starts slowing down, and reaches its slowest speed here. And if we're talking about the solar system, that's the helium from Helios, the sun. Where it's the Earth, it's the apogee. And the space age, when it was very young in America, perigee, here's the perihelion. If we're talking about the sun, if we're talking about orbiting the Earth, it's the perigee versus perihelion. And then if you're talking about Jupiter, it's the perijove. And if it's the moon, it's the perilune and the apollune. Orbital mechanics and flight mechanics, enough of these. We're not going to name them after all these bodies. They have a generic name, the paraapsis and the apoapsis. It sounds like a disease you have down here. You know, I have a paraapsis here and I got to get it x-rayed or something. So, but that's the generic, paraapsis, apoapsis. But what Kepler did by brute force, he said, look, every ellipse is a little different, but is there a simple way? Ellipses are just distortions of a circle. So can I take circular motion or elliptical motion? This is the one in the gray that has the gray interior. You know, it speeds up going around the bow, and then it slows down. But is there a circle that has the same period, same amount of time, but I can transform from a circle down to the ellipse? And he said, yes, it's called the Kepler circle. And here's the geometry, and he relates it all. The mean anomaly is just the amount of time it takes to go make one period. E is this angle. It measures, here's the planet on the ellipse, but if you drew this line upward, let it touch a point on that circle. If you follow the points on the circle, you can relate it to where the planet is, and it's much simpler. And he came up with an equation. Let's see if I'm going to hit the button again. No, I don't have it here. He found a way to do it, but it's Newton did the same thing. And it's a way to measure or determine for any given time, I know where that point is on the circle. I said, well, that's great, but I don't need it on the circle. I need it on the ellipse. Then you have to go to more math, because for mathematicians or orbital mechanicians, they start to focus this new angle. I need to know that. That's called a true anomaly. And I need to know at what time that is, because this R distance locates planet. It's R distance there from the focus at this angle. But if I use the circle, I can just do it easily. The thing is, it's too hard. You cannot solve the equation. There's no closed form solution. So Kepler had to do a numerical guess, and Newton he was so smart. He invented parts of calculus. And he said, I know how to do it. The Newton-Raphson method, how to approximate with numerical estimation with very, very good accuracy and precision. So they could solve all this. Remember, Newton was doing this in 1687. His laws were the ones we use today. They're not changed. I mean, we don't need Einstein yet for this stuff. We're still using them unchanged. We just use millions of them for, like, the equations that describe the vibration of the Orion spacecraft, 20 million equations for the structure about how it vibrates. And the computer solves them simultaneously. You know how long it would take me to solve 20 million equations simultaneously? I don't have the units for the time, so I don't know how long it takes. Several lifetimes, I guess. Now, even though I drew an ellipse like this, any squishy ellipse that fits in the circle, any kind of ellipse, you can fit it into the circle, as long as the periods are the same. All right. So Newton did his book, the Principia, the Mathematical Principles of Natural Philosophy. Remember, he was not a scientist. That said, I'm a natural philosopher. I think he wrote it in Latin. And if the Three Stooges wrote it, they'd write it in Pig Latin. So let's see. It had the 3 laws of motion. Can we name them? Like, I think I have them written somewhere else, but first law of motion is every object that has mass moves in a line or in motion that's essentially a straight line at the same speed forever until I'm interrupted by a force to make me change. The second law is this right here. If there is a force, it's described by the inertia times the change in speed and direction. We call that acceleration. Any change in speed, it may involve also change in direction, called acceleration. What is inertia? Well, we say mass, but what is that? It's a degree of, I don't want to change my speed or direction. It's a measure. The more inertia I have, the more stubborn it is. I don't want to move. I don't want to change from my original course. Inertia. The third one is the action reaction. So I'm going to point out something that looks funny. If this is true, and Newton thought of these as point masses or lump masses, he also knew that real bodies are collections of mass. We can mathematically, well, a real object has got lots of point mass. I can model this in my mathematics with lots of points in here. But let's just take 2 points. This is funny. These mass particles, they may have 0 dimension or very tiny. Yeah, I can have bunches of them to measure, describe real objects. But what if the distance r between any real masses becomes smaller and smaller, approaching 0? This implies the force gets as big as we want. It's approaching infinity. Like, do we need Einstein or quantum mechanics to get us out of this? They said, well, real objects really bump into each other, and they don't. Well. What about a proton and a neutrino? This says that when they get, it did like that M1, M2. There's nothing saying how big or little those M's are going to be. It's this R that's the problem. You start getting that too big, too small, you're almost dividing by 0. So what the heck? I can make if I'm at the center of the sun and a proton approaches it and it gets too small, I'm getting infinite force between the proton and the sun. Oh, wait, what's going on? So there is a way out of this. Is it infinite force? Is it the universe doesn't like singularities? We're still in the Newtonian world here. We'll continue this a little later, but think about that. I don't know if Newton did, but we're going to get to that. So this slide here is just little consequences of the motions of I'm not afraid to show math here, and I hope you're not afraid to see this, because part of my motivation here is STEM, they're young people here to keep going in their education and to challenge themselves with more mathematics and to keep learning. Also for those that say, I don't like math, I'm left-brained, right, left brain. I don't kind of believe that stuff, but you can. But I think there's social messages that have told people they're not good at math or they don't like math. And I'm telling you that if you learn the physics and some of the math, like the structural dynamics that I have, if you're experienced, you can look at an equation, and I don't have to solve it. I hate plugging in numbers. I don't like arithmetic. I hate arithmetic. I don't like dividing and adding and multiplying by hand. I hate it. But symbolically, we can look at an equation and say, that's oscillatory motion hydraulics. It's described by sines and cosines. Another one, that's impulse. Collision, a hammer blow hit an object on a spring. It will have pure sine motion, no cosine motion, just pure sine motion. Right away. That's a quadratic equation. It has two solutions, and they're two physical, real solutions. That's a cubic equation. That means it has 3 solutions, 3 roots, and on and on and on. Sometimes in your field, you can tell immediately, I didn't even have to solve it. It speaks. It's like music. They're like notes on a music sheet. They're telling you the character of the solution, of the response, without even plugging a number in. So from Newton's laws and the law of gravity, you get the circular speed of a satellite. It's the square root of g newtons The M is the Earth. If we're talking about the Earth, plus the R is the distance from the center of the Earth up to where the satellite is. So let's say this is the Earth. This is inscribed at one of the U.S. Air Force, the Canaveral Air Station near Kennedy Space Center, some of the old Mercury launch pads. This is engraved down there on the cement, this formula. I mean, you can't go there. I mean, I went there and it was grass covering it over, and I don't even know if I was supposed to be in that area, but I drove over there. Wow, look at that equation. It's carved into the cement, not paint. It was dug deep in the cement there forever, for forever. And I don't know if anybody reads it or the grass cutters go, I wonder what that means. It's how to calculate tariffs or something. I don't know. Well, that's the circular speed forever and ever and ever until you get drag or something interferes with circular. But I want to escape. Well, all I got to do is multiply with square root of 2 times the velocity, and you escape. You hurl away into parabola or hyperbola with respect to the gravitating body, like the Earth. No, they didn't say the sun. The two-body problem. Whatever you're going around, when you move, you're now moving away and escaping, and you won't come back. So whatever goes up doesn't always come down as long as you multiply by the square root of 2. So I like square root of 2 is take a square, make each side 1, 1, 1, 1. Well, that's the velocities you have going around the Earth. I want the diagonal of the square. Make it that long. That's the velocity vector. Square root of 2. Multiply by that. I'm gone. I'm out of here. No. The other thing is, what if I'm capricious? What if the escape velocity I plug in, make it the speed of light? That's this is Newtonian physics. If you plug that in, what is R for that? I know the math. Maybe it's the Earth. Maybe it's the moon or the sun. If I solve for R in this top equation, I'm getting the Schwarzschild radius. I said, but wait a minute, this is Newton. He didn't know about Einstein, but the German physicist who came up with the first closed form solution of Einstein's equations, Schwarzschild means black shield. Schwarzschild tragically died in World War I. He was a brilliant physicist, mailed the solution of his closed form solution to Einstein, and Einstein was, I'm amazed. I did not know somebody would come up with a beautiful, elegant solution so quickly within just a couple of years. But Schwarzschild died in the war. Tragic, brilliant physicist. I think he died of his wounds in artillery or something like that. Well, it's the same. It's the same formula. Maybe somebody else can explain it, but I'm intrigued that it's the same. You get the same answer with the Schwarzschild solution or Newton, and you specify mass, and it's the radius. That's where if you get any smaller than that radius, it starts collapsing into a black hole. So for a human, it's like microscopic, real tiny. For the Earth, it's something like this big. For the sun, it might be a few miles across. But of course, you can't imagine what would compress it down to that size. There's no explanation. But I'm just intrigued that Einstein and Newton agree on this here. That's where the object, Schwarzschild's radius, is where the event horizon would form. And I have examples here. The sun's Schwarzschild or Schwarzschild radius is 3 kilometers radius. Earth is about 0.35 inches. Moon is about 1/10 of a millimeter. And I'm just noting here, this was referenced in the Homer Simpson episode, season 18, episode 4 is the Blob. And he reached the Schwarzschild radius too. But he had assistance of an extraterrestrial mysterious substance. So the first human to achieve that. All right. There's other things. I wanted to pile so many things that are consequences of Newton's laws and the gravity. This is just one of them. These are the Lagrange or libration points. Let's say it's Earth and Moon. You can have them between any two bodies, but let's say Earth, Moon. You can do Sun and Earth, and several of the big space telescopes. The James Webb, I think, is at one of them. That's Sun, Earth, I think. So what you get if you have a two-body problem, flat, bodies are not necessarily behave like that, but let's say you have Earth, Moon, and Earth, just the plane that they make. The standard nomenclatures to name the ones that are collinear, like you draw a line from the Moon to the Earth, you get L1, L2, L3. Those are the collinear points. L4, L5, or 60 degrees. If you drew a line horizontal like this, the angle up to that one's 60 degrees. The angle down to L5 is 60 degrees. You write all the equations of motion, and the books introduces, they call it the circular restricted problem. They say, take a satellite like going around here, and it's of negligible mass. It cannot disturb the Earth and Moon like the James Webb Telescope or a spacecraft. It's too small and puny. It can't. But the Earth and Moon dictate the orbit of that satellite or the spacecraft. So that's the third option. You need three bodies: big one, another big one, and the little one. The little one, you write all the equations when they really look hairy. They're very elegant looking. Now you try to find solutions like this occur, where it's like painting dots on our old record, like a record platter, like LP albums of the old days. When it's going around the spindle, all the points are moving together. They don't move away from each other. They don't collapse. But there's only 5 of them on that platter. Not every platter and all the grooves of that old record. Well, I got a dish here. So this is rotating like the old record player. There's only 5 points. You draw them just like I did here. And let me go to this next one here. The ones that are in a straight line, they're unstable. What does that mean? They're too emotional. They wear their emotions on their sleeve. No, they're not stable, meaning the slightest disturbance, the other planets pulling on them, what are the 2 biggest gravitational disturbers or the big ones in the solar system?
Jupiter.
And the sun, right? The sun and Jupiter. The rest is just microscopic dust motes. They have an effect, yes, over the long term. All of them do. All the planets, everything, all the masses. But in the short period of time, Sun and Jupiter, maybe sometimes Saturn, they dictate the perturbations. But there can be other disturbances: solar wind, radiation effects, the Yorba effect or something like that. And if you're doing the Lagrange points around the Earth isn't perfectly spherical. It's got mass concentration. So does the Moon. It's not does not have a perfect symmetric mass distribution. So they're causing little disturbances too. So the people that derive these have to account for more effects. So if you put things there at L1, L2, L3, they're inherently unstable. But the ones at L4 and L5, they're very stable. In other words, if you disturb them, just shove them a little bit, they'll wander out of that point a little bit, then they come back, and they'll just oscillate around there. L4, they're stable. But I think the spacecraft we're using are collinear. We're placing them there because maybe for observational reasons. So because they're unstable, you have to have a fuel supply for that probe. You have to have for that spacecraft. You do have to expend fuel to keep coming back. You wander out of that point. Now, look at how the artist drew this. It's like a ball. Pretend there's gravity pulling down. You're putting marbles there at L1, 2, 3, 4, 5. People say this wrong, even sometimes in NASA papers or it's really public affairs. They say it's where all the gravitational forces are equal. No, that's not true. That's partially true. It's where the centripetal forces balance the gravity forces. The gravitational forces are balanced by the whirling around centripetal accelerations. It's that acceleration you feel on the merry-go-round or the carousel. It's pulling you toward the center of the hub of the spindle, that circular motion. But when those are balanced, it's like you're putting marbles on this surface, these little islands where they're perfectly flat. And see those big wells? That's the sun. That's a big gravity well. Where Earth is over here, blue, that's another gravity well. You put a marble near there, it's going to fall in there. You just move it, it's not stable. But look at where L1, L2, and L3, there's a little islands like right here where it's a little flat, it's flat enough, but the slightest disturbance makes it fall off one edge or fall into the hole and fall on. But L4 and L5, they have larger islands. They're more tolerant. They're flatter. But you can generate these mathematically from the equations. You can just say these little islands of stability and instability, but it's like putting marbles on these curved surfaces. All right. This is fun. This is not, some of this is Newtonian. I was sad that Dr. John Dyson passed away in 2020. I thought he was still alive, but that means he'd be 100 years old or more. His ideas have been used in science fiction novels, stories, and also a Star Trek Next Generation episode, a whole episode about a Dyson sphere. The idea is, suppose you have an advanced civilization, or their planet, they've developed advanced technology, but they want to use all the energy of the sun, that they're orbiting. So if it's in the Earth, if we're talking about the Earth, the Dyson sphere encapsulates the Earth, and here's Venus and Mercury in here, and it's got, I'm not vouching for these dimensions here, that's this thick or that, whatever. It surrounds the entire, just the sphere. You're capturing all the energy and we get to use it. And why do you think it has infrared radiation arrows there? What is that for? What's it indicating there? The shell heats up. You're capturing all the energy, but it's going to heat up and it's going to radiate infrared into space. That's one signature where I think some scientists or people think, can we detect a Dyson sphere? Maybe the planet's outside of it. They're orbiting an empty space, but it's not a black hole. It's empty, and there's a infrared signature, a lot of infrared. But where's the sun? Where's the star? This could be a clue that this could be happening. And let's say we're inside a fictitious Dyson sphere, but let's say it's a shell of matter. Let's just say it's a shell. It could be a Dyson sphere, but I'm going to take any shell. This is a thin shell of mass. I'm trying to trace this red thing here. It's uniform mass density, but I put some test particles in here. So here's one. Let me pick this one. It's near the edge. Near this inner surface of the shell. So that has mass, and so does the shell. What is the force between the shell and that? Is it, if you let it go, let free, would it start, how would it move? Would it start approaching the shell surface or float around or what? Let's say I just put it there. No desire. At rest, I just put it there, let go. No desire. What would happen? What would happen? Pardon me? No. Okay, that's one answer is nothing. If I put it at the center, let's say that's the center, dead center, the centroid of that shell, I put it there. What force does it feel? Gravitational force. I hear zero in all of it. So, okay, feel all the mass, all the force of the shell, and other zero. Okay. Then I have one that's outside. What would it feel? Outside the shell. These are old questions. So yeah, maybe so. So let's take that latter one. In dynamics, my dynamics books, they take collections. It's kind of a very easy derivation. You can assume that this is just a bunch of masses strung together in a sphere. It turns out no matter how they're arranged, a sphere or lumps or a cloud of lumps of mass, if you're outside over here, all of this can be described as one mass called the sum of all the masses put at the center, the center of mass point. For a distant particle, you're looking at a mess of a beehive of hornets. You get far enough away, and I have my measurements all I see is the center of mass, or feel the center of mass of hornets. I don't care about each individual hornet. Just lump them all together into one mass and put them at the center of their hive. That's what I feel. That's the same thing with any collection of masses. If you're far enough away, that's always the case. Now, inside, this is out of my physics book. This is a calculus derivation, but here's a little mass particle, and it's inside the shell. They go ahead and subdivide it. It's a uniform density. There's the result on the right hand, 0. So that means anybody inside of a shell, whether you're, I'm going to go back a second. Hold on a minute. I'm supposed to do it this way. If you're inside the shell, it's 0 force. Some people feel like, well, if I'm close to the wall, like down here, the wall is pulling me in. Well, it is. This near mass, the law of gravity says, the inverse square law says it's stronger. It should pull you in. But look far away from the wall. There's a lot of mass out there. It's further away, but the collection of all that mass is canceling it out. So no matter where you are inside the shell, it cancels out. So you would just feel nothing. Now, you've heard this probably, this is old. I'm going to drill a hole all the way to the center of the earth and go out the other side. And I'm going to jump in it, or you are, or we're going to drop a live pig in it or something, instrumented pig. All right. Now we know there's magma and there's tectonic forces and there's heat and all that. So the tube is made out of unobtainium. It's in all the movies. I can vouch for that. In fact, they were mentioned as a movie. It was a Hilary Swank movie called The Core. It's about going to the planet, and they said that. They asked, what is this made of? Because our submarine will melt and we're going to go to it's unobtainium. Okay, it works, It can't crush, and it protects you from the heat and all that and radiation, because you go to the core of the earth, there's thorium and liquid uranium. You're getting irradiated, but unobtainium protects you from all that. So we do that. We have this tube goes down center of the earth. When you go to the equations of motion of using the fact that there's a shell, anything outside the shell, I said that I could look at the shell as being a point mass. I can collapse it down to the center of mass. So when I'm outside the shell, it just acts like another point mass. But if I'm inside the shell, it's 0. I feel nothing. So when you go through all those equations, combine them together, and it's down here, you get a spring equation, something that in my structural vibrations, when I look at it, it's called a second order differential equation. It says, oh, it's spring motion, just spring motion. So if you jump in, you will fall. But here's what's happening with these shells. As I start falling in, all the mass above me and around me, I can say they're shells. They're not having any effect on me. It's only that inner part. As I start falling, like here's the particle. If I fell this distance, I don't know, a kilometer or whatever, I'm at this point, this mass in the interior is pulling me in. But this outer stuff, it's like those shells. They're not doing anything anymore. So it's until I get to the center, then it's zero force. And like a spring, it starts uncoiling the other way, and I start moving to the other side. So without damping, if I don't put damping or friction or anything, I'll oscillate forever. I'll just go to the center of the earth and I'll reach maximum speed there, maximum speed, and then come up to near zero speed at the other end of the earth. Then I'll rebound, go back, reach maximum high speed at the center, slow down, go to the other side. I'll just oscillate forever. So, and I've derived this myself. What is that maximum speed? It's orbital velocity at the surface of the earth. If you could remove the atmosphere of the earth, no drag, and get a rocket or artillery shell like Jules Verne did, get me at orbital velocity right above the center of the earth, the surface of the earth. I'll orbit forever at the same speed that I reach at the center of the earth. So it's like if I take a circular orbit and project it sideways onto a screen, I'll see a spring motion. That's what an orbit is. If I'm going around the earth like this, and I've got a light beam on it, like a light like this. I'm moving around like this and I'm shining it on the wall, this light beam. The light beam on the wall, the spot would just go up and down, just like I'm moving through the center of the earth. So imagine there's a flashlight going around like this. It's the same thing, sinusoidal motion. That's the spring equation that I use in structural vibrations, and you get a frequency out of it. And even though mass appears there in this equation, the K term has a mass, the masses cancel out. Now, how about tangential motion? So jump through that tube of unobtainable, I get spring motion. But what about at right angles? You said it's kind of like a spring, but what about going, not just doing this, but what if I'm inside? What about tangential motion? When you write the equations of motion for that, you have to put in centripetal acceleration, then this spring term right here. I'm not saying you know how to do that. You work it all out. The masses cancel out. It says it doesn't matter what your mass is. I'm inside for tangential motion. M and R cancel out. Theta dot is the angular motion. Theta dot it's a term. It just said the angular speed. How many degrees over unit of time? How many degrees per second? How many degrees per minute? Or how many degrees per year? It doesn't matter what the time. The rate, the angle is changing. M and R go away. So, what the heck? What this says is when I'm inside these shells, there's no gravity. The implication is if I could orbit the center at constant angular rate. And that actually happens with dark matter. Most galaxies are immersed in clouds of dark matter. They don't interact with regular matter. They're like the infinite shells of dark matter. You're not running into them. They don't appear in our detectors. We can only sense it gravitationally. They warp light. They warp space, and they cause light to distort for distant galaxies. But scientists discovered, and what's her name? Vera, the scientist. Yes, Vera Rubin. When you immerse ordinary objects in dark matter, like the galactic motions, the spiral galaxy, the stars near the center of the galaxy, they're kind of Keplerian. But if you move away, Keplerian, like Newton's law of the solar system, when you move away from the center of the galaxy, the outer stars are moving too fast. It's like I plotted here, the center of the galaxy. Every point on this stick is moving the same angular speed. The outer point of the stick is moving faster than this one in here. That's opposite to the solar system. Mercury moves the fastest. Uranus and Neptune and the Kuiper body are really slow out there. Dark matter reverses this. They're moving faster the further out they are. So this is one of the evidences. Even Newtonian mechanics can kind of show that. That was the big evidence that was happening. Brachistochrome problem. That's another one. That's just, I'm going to go fast here. The Bernoulli brothers, they were natural philosophers, said, how much time, Doug? Or want to wrap up? I'm 20. Okay. This is just a curve. What is a curve that meets minimum distance, right? What's a curve that go from a height to go down and at minimum distance? Well, the Bernoulli brothers said, all you smart people of Europe, everybody do it. And it turns out it's a cyclic, and you see some balls released up here. There's a line, parabola, but only the cycloid has that minimum time. There's some delta t later, a little time later. All these balls are racing down to this point, but now the black one on the cycloid is the one that's going to beat them all. Newton discovered this, and so did some people in Europe. They took a long time, weeks or months to do it. Newton found out about it late. He did it overnight. He had a headache or whatever. He did it overnight, mailed it in, didn't even sign the paper. And Bernoulli said, why didn't you sign it? He says, oh, I knew I could do it. I hate when foreigners question my work. So I don't want to argue with people. I know I could do it. I'm a genius. Everybody says I am. So, I'm concluding. I hope we keep having a human presence in the solar system. I happen to work on the autonomous landing and hazard avoidance technology. When we were blasting this little Morpheus rocket here at JSC and at Kennedy Space Center, I like this. Maybe we'll take our pets with us in the future. We got to make little suits for them. And then who gets to the moon first? Well, somebody's going to go. It's going to be one of these three, or we're going to hold hands when we get there. You know, Russia and China said they're going to build a nuclear reactor there, but it's for everybody. But okay, then what do we do? Okay. And it looks like the man in the moon doesn't like what's happening. You know, this from that old silent movie, Trip to the Moon. We'll probably go to the South Pole, and then eventually maybe we'll reach this goal like this gentleman. I used to see him on the Walt Disney program, Das Mars Project, and I'd see all the shows about Von Braun and his space stations and missions to Mars. And it's one reason I got interested in real space in the 50s, because I watched Von Braun talk on the Disney programs a lot. And thank you very much. This is one mission I worked on, a rescue mission on shuttle program. We never had to do it, but it was hypothetical, but I was proud that I'd led that little tiger team just in case we need to do it. Any questions? Thank you. And Doug, you tell me if we have time for questions or not. One or a correction or, well, thank you. Thank you much. Thank you.
Okay, so Rick's got some Sky and Telescope magazines up there. They're free. We're talking to you, Rick. Up there, right? You get no. I'm asking you about your Sky and Telescope magazines. You brought them, right? Okay, so they're up there.
Yes.
Okay, so there's a free Sky and Telescope magazines up there that Rick brought. All righty. After the meeting, we'll get together at Mod Pizza. Everyone, I want to be clear, everyone's welcome to come to this. You shoot up Middlebrook, take a left on Clear Lake City Boulevard, right in front of HEB. There's a Mod Pizza. We'll get together and talk about astronomy and other topics, but everyone's welcome to come to that. We will take a 5-minute break, and then we'll get back together for the second half of our meeting. There you go. 5 minutes.
Thank you for that. And the photo. Well, thank you. Yeah, the ones that don't have a location. Yeah.
I see that.
Okay, 5 minutes is up and we're going to get started. So obviously it's not working. Okay, we're going to get started with the second half of our meeting. Okay, we're going to get started with the second half of our meeting. Third call. I'm coming to your classes. I'm telling you, I'm going to do the same thing. We're going to try to get started with the second half of our meeting. Fourth time. Okay, we're heading. We're going to try to start the second half of our meeting. So, guys, there's going to be somebody up here talking. You can't talk at the same time that the speaker is presenting, right? Everybody shut the hell up and let him talk, okay? All right, now.
Are we doing this thing first? Or not?
Next up, we have Rick,
Okay.
who is doing what thing first?
Yes. Giveaways, or is that later?
Let me do that at the end. I know this is the first time you come to one of our meetings. Okay, Rick is going to give us, tell us about, could Jupiter have been our second sun? He's going to give us a quick presentation about that.
And I'm going to do the very best I can on this. Okay, so actually, I had thought about this before, and it just popped into my head one day, and I thought, you know, Jupiter's pretty big, and in all honesty, I don't remember seeing a really good comparison of the Sun and Jupiter done in a picture before. So I'd always see Jupiter's big and the Sun is bigger and everything. And I thought, you know, I know it couldn't be a second sun, or it would have been, but how close was it? Is it something that was fairly close, or was it, you know, there wasn't a chance in the world? So the first thing I did was I went and using units, and I believe I just go down. Enter. Oh, just hit enter. There's enter. Okay. Oh, that's not it. That's not it. Anyway, the first thing I did was I put a picture with some units, actually the diameter of both of those, just to see what, just to see how they compare. And I had a hunch that, oh, there we go.
This one says enter. E-N-T-E-R. There you go.
Thank you, Doug. You know, it's exciting to have here as our leader. Okay, so okay, so I honestly, when I saw this, realized, hey, I've never actually seen a picture, or don't remember seeing one, where it actually kind of told you. And of course, when I saw this, and it's about the interesting part is the sun's mass is 1,000 times the mass of Jupiter. And at that point, I thought, yeah, I guess they were right. It's just not big enough. But it was interesting to see it anyway. The next thing, go to the next picture. Okay. So I said, all right, well, are there any other factors that fall in there? So I decided, well, at a very high level, I'm just going to kind of go through the different steps. And there were some steps in there that I'd never heard of before. So there we go. Okay, so the first thing, and everyone really knows this, but it starts out with a nebula, and it's consists of dust and gases, and primarily hydrogen and helium. Okay, so at that point, you've got the dust and gases, and they start to form, and they start to clump together. And the bigger the gravity, the more the clumping that occurs. And then doing a little research, I realized that for us to actually get to a point where the sun could even become a sun, or Jupiter could become a sun, it'd have to be about 8% of the mass of the sun. And I was pretty sure it wasn't that, because it was 1,000th of the sun. But I kept on pushing. And there we go. Okay. And at 8%, there's sufficient gravity that it's able to start creating its own heavy hydrogen. And the next slide, I'll show a little more about that. One thing about heavy hydrogen, during the Big Bang, that's where most of the heavy hydrogen was created, and it was thrown all over the universe. Next. Okay, so we've got a hydrogen atom there, and it's got a proton and an electron. Now, heavy hydrogen, or deuterium, and it's called a couple other things too, it has a proton and a neutron. So the way this happens is you take two hydrogen atoms, and under immense pressure, you clump them together. And what happens is one of the protons turns into a neutron, and the other one remains a proton. And so that's how you end up with a heavy hydrogen atom. Okay, I think I missed my thing, but are we missing one here? One of the slides? How do I go back? Next, please. Oh, there we are. Okay. All right. So at any rate, one thing about the deuterium is that it ignites at a much lower temperature, and that temperature is about 1 million degrees Kelvin. Enter. Okay. And of course, the deuterium is going to be double the weight of a hydrogen atom. And so it's going to, through gravity, it's just going to migrate itself down to the inner core. So eventually this gravity causes the new star we call a protostar to collapse in on itself. And it collapses in on itself, and as it begins to heat up, hits 1 million degrees Kelvin, then the heavy hydrogen will ignite or fuse. Okay. At that point, the heavy hydrogen starts burning, and when it does, because it's burning, it's basically pushing itself out. You've got gravity trying to push itself in, and it reaches sort of an equilibrium there. And of course, at the same time, as it's pushing itself out, it's expanding that protostar, gathering more hydrogen as it goes. Then we hit the final phase, and that's where the deuterium burns out, or most of it burns out. And at that point, you don't have that equilibrium anymore. It starts collapsing again. At that point, it's still absorbing a lot of the hydrogen. And so it will basically compress, depending on the amount of hydrogen that's there, it'll heat up and then fusion begins. And the one thing about it, and this was interesting as I was researching it, I would research it and basically I was Googling, hey, what temperature does, hydrogen start to fuse at? And they gave me numbers like 10 million Kelvin and 100 million Kelvin and 15 million Kelvin and 14 million Kelvin. But what they didn't explain, and I actually had to go to one of my physicist friends, is what's actually going on here. I know there's big gravity and little gravity, but how is that part of it? And it was explained to me that basically when you're dealing with high gravity, the temperatures could be as low as 2 million degrees Kelvin to begin fusion. If you have low gravity, the temperatures might have to be as great as 100 degrees Kelvin to begin fusion. Okay, so from there, this is the picture I had before, which is pretty realistic on what the comparison of the size is. And as it turns out, that's how big it would have had to be at a minimum 8% of solar mass. So from a visual standpoint, it would have had to be a lot bigger. So in conclusion, it's not nearly big enough. In fact, it turns out it would have to be 80 times bigger for it to meet that 8% solar mass to have had any chance at all of becoming a second sun. So in conclusion, it just never had a chance. That's it. Did I do it in 5 minutes? Anyway, it was fun putting this together.
Up we got.
Yeah. What? No, because there was nowhere, and as I understand it, it would have had to been 80 times bigger. So it wasn't even close. I was hoping it was close. Maybe it could have. Pardon? Yeah, in the infrared. Yes. Well, I think I would have to go to Justin here, who's much more of an expert.
The smaller the body of mass, the higher the temperature has to be, because with high gravity pressure, you don't need as high a temperature to do nuclear fusion. Actually, brown dwarfs engage in deuterium fusion, not hydrogen fusion, so it doesn't generate as much energy as hydrogen fusion. But it's still, you need a lot of mass. And Jupiter does not have the sufficient mass to undergo any fusion. You need at least the theoretical limit is like 7.67% the mass of the sun. So you can compress the material at the minimum of 10 to 13 million Kelvin to undergo deuterium or hydrogen fusion.
So it's the image, but it's really.
Yes. The accretion, the material squeezing in on itself.
Thank you.
You got Forrest got questions. So
That protostar phase for doing deuterium fusion, like for a main sequence star like our sun, how long does that last? Is that like a billion years, 200 million years? What?
I'm going to defer to Justin.
We're referring to what? The
One, in the talk, it went through a phase of the protostar where deuterium fusion happened, and then that stopped, and then it started collapsing again, and it started hydrogen. How long is that period for, say, a star that's the mass of the sun? Like
And I actually Googled that. So I did all this. And they gave no information. There wasn't even a guess on that one.
it's highly theoretical. They put it anywhere from a few 100 million to a billion years. You have to remember that the sun's temperature is increasing and the radiation output increasing over continuously from every gene sequence life. And then as it slowly swells, eventually in about 600 million years, you won't be able to have oceans on this planet because the radiation output will be 30% greater. So it's I'd say about several 100 million years for it to go from the protostar into the large size. But it will vary based on the star's mass. It's a very complicated equation.
And I have to tell you, as I was researching this, I kept it very simple because it's a very complicated process. Anyway, thank you.
Any other questions for Rick? Okay. Next up, got Al with What's Up in the Sky and recent astronomy news.
I just love all the physics. And now there's something different. It's not physics. Let's see. The very first thing I always touch on is meteor showers. I brought this up last meeting. And so we have the Aquarius meteor shower on the 18th. Was that coming up in a week? And most of these all last quite a bit of time. Some of these, they don't really list what the high point is, like what the best date is. Okay, our first binocular objects. So I'm migrating across the sky doing the constellation or the zodiacs, and we left off with Libra, and now we're over to like Scorpius. And I've been noticing I've been calling it Scorpus and not Scorpius. I've been leaving the I out for, I think, this last year. But anyway, so M80. This is twice the number of blue stragglers compared to most globular clusters. And this was discovered in, oh no. And so there was a famous supernova that occurred in 1780. So why is that particular? Well, because I'm trying to find something interesting about all these globulars. There's so many of them, but what makes one different, or what are people studying in some of these objects lately? So this is M19, another binocular object, fairly large. This one is unique and different. You can almost see in the northern direction that it's a little bit elongated, and they think this is because it's near the galactic core, near galaxy core. And so they think that at some time it was stretched. If you look at models of the globular clusters, they show them basically going in and out of the galactic plane and migrating and moving around quite a lot over millions of years. So it's not surprising that ones near the center would get a little bit disrupted. M4, crab globular, and this is also in Scorpius. This is distinct because it has a lot more white dwarfs in it. And if you notice in this picture, you don't see quite as many of those blue stragglers. Blue stragglers are much more massive stars that, instead of curving on the HR diagram and staying with the track of going into red giants right away, they have a tendency, because they're so big, to continue further away from the HR diagram and then curving kind of later on in life. And so because of this, they tend to change colors and have this kind of blue emission. I don't think that we can see any of these visually, the blue part. I thought that would be really exciting if we got a chance to like see some of these blue stars. I know there's blue stars out there, don't get me wrong, but in these globular clusters, I think it'd be really cool to actually see those blue polka dots. Okay, the very first telescope object is a planetary. This is, I don't think I've been able to see this one. This one's a little bit fainter. And it's unique because it has a binary red giant and a white dwarf in the center. And so most of the planetary nebulas, remember, planetary nebulas weren't supernova, they were just regular nova, which means they collapsed, and then there was a problem with the physical structure such that it started outgassing and spewing out some of its material. And that's why you get these interesting shapes. It's not a supernova where it explodes, those are bright for a certain period of time, and then they dissipate so fast you don't get any kind of a cloud or anything else. And so that's what's neat about this one, is it's a binary. This is also another cool one. This one's hard to see. So I picked a few objects down in Lupus. Lupus is a very low constellation. That's basically where Omega Centauri is. Because Lupus is kind of obscure, it's very low on the horizon, but it has a lot of cool objects, has some very interesting galaxies and some planetary nebulas. This is kind of between Lupus and Sagittarius, little gem. This has just a very unusual shape. Usually they're somewhat related to a circle, and this one is more of a parallelogram. And then we get into a couple other objects. This is a galaxy in Lupus. This one's a little faint. This one's a little harder to see. But it is one of the few barred galaxies. It's one of the things physically, you know, we have all these great pictures of barred galaxies, but visually there's very few barred galaxies we get to actually look at. This is one of the very few. I think there's less than a dozen that you can actually visually see very well. And then to close out our telescope objects is an ARP galaxy. Well, no, I'm not on that yet. I think I got something a little bit mixed up. I'm going to go forward. Okay, this is at the ARP galaxy. I took out one slide, but then I didn't take it out of my notes. And this one's really cool. It's another one of those faint objects around 14th magnitude, so it's pretty hard and obscure to see. But once again, it's got a lot of cool structure. I like in the ARP galaxies, you know, things that have irregular shapes and something interesting. This one I don't think I've seen yet. So recent astronomy news. I have a few good items here. So once again, you know, James Webb Telescope is just coming up with so many new things. And in this one, you know, I think it's just so cool that they're studying so many obscure things. You know, we wouldn't even think that with telescopes we could see such things, but they're looking at some of the dust shells around massive stars. And the reason why is planets, right? So they want to keep studying the planet phenomena and try to understand more about it. So being able to visualize the dust and the chemistry around these young stars is very interesting. So this is, they didn't do that here, but very often they use it in combination with the ALMA, which is the radio telescope array, and it has really good precision too. So next one is, this is really cool too, the cosmic owl. So once again, you know, when they go in and they're looking for these really faint, obscure objects, and this is a rendering of it. I have a picture of the actual object, but this shows you the different components in it. And what's really cool is they have two basically like ring galaxies that have collided, and there's a couple of jets coming off of it. And once again, the reason why they study these aren't because they're really cool, but because they show some dynamics within the galaxies that you wouldn't if you just had a static galaxy. And so by looking at the chemistry and what's going on in the interaction, that's where the science comes in. And so this is really cool. I didn't get a chance to figure out what they're using visually to see this, whether they're using combination of the ALMA and James Webb telescope or not, but it is just so cool. Okay, we're getting there. And this is another really cool thing. This, I've never heard of this. I think they're continuing to come up with new terms for some of these galaxies, because as they can peer further and further into the cosmos, we're starting to see more clarity in some of these galaxies. So they've come up with this term, a jellyfish. And what's very interesting about is these young stars, you know, around the outer perimeter here that are in the circle, in these circles. And so they're really kind of looking beyond the galaxy itself and trying to look at some of these things. Once again, the unusual aspects of the things that they're spotting give them clues as to evolution and changes in physics and the dynamic nature of galaxies altogether. This one's really cool. So this is a static picture. This is the last one. So once again, planet formation. So they're really looking at these protoplanetary disks. And so using, the James Webb and the ALMA, they've been able to go in here and get good images. There's so many here, really good images of the protoplanetary disks. And then check this out. So the interesting part about this is they said that it was a Bachelor of Sciences student, maybe, maybe not, but they created this Python code to go in and tweak the pictures. Now, I didn't get a glean on exactly what the procedure is. Sometimes they're secretive about this, but kind of try to pull out a sharper, more defined image. So in this next slide, you can see how this switches between the two different modes. So they're looking at spatial resolution, and some of these, they just look like blobs. And as soon as they put this program on it, then they get sharpness and detail that's just incredible. And I don't remember, sometimes I want to go and research so many things. It's like, well, when did we get the first picture of a protoplanetary disk? The precursor to planets, it's like a baby or a child, when can we see the beginnings of our solar system, so to speak? And so I think that's the big question in everybody's mind. Thank you.
This will be pretty quick, actually. Oh, that's right, return. We had absolutely nothing last month. About our next event, August 1st, Friday, would be at the Hack Winery. I've already checked that. There's going to be a decent moon available. So unlike the last time where our moon was, we had to wait for it quite a bit before it actually showed up. September, Okie-Tex, again, with another one with a hack. And then we kind of finish out the year. As you can see here, I won't belabor them all. At the very bottom, I do have some dates ongoing with Armin Bayou, which will be good. We'll get a couple of them there. Dan Roy with HAS has an event at Challenger Park next Friday. If you wish to participate in that, he's already posted it on the list. But that event's going to run 8 to 11. So there you go with that. The hot news, fresh off the press as of yesterday, that I couldn't get into the slides, is we've already got our 2026 fork dates nailed down. 19 through 23 in March, and then I don't recall the exact dates for October, but those dates are already set. The cool thing about the March dates is I was also approached by the president of the San Antonio Club, somebody from the Austin Club, and then also somebody from NHAC, North Houston Astronomy Club. They all want to 4 clubs converge at the fort in March of 2026, 19 through 23, and do a 4-club Messier marathon, which would be kind of cool to do. If you don't know what that is, Messier, as we know, was a French astronomer, came up with 110 objects that he thought were boring because they weren't comets, when in fact he was handing us the 110 best sought after list in the sky. But at certain times, mainly March, not so much October, mainly March, if you start right at twilight and you do it as a collective group, you can look at all 110 in one night. And people will go, oh, I've got M such and such. And everybody runs over, looks at it. And somebody else comes over here, oh, I've got M this. And they all run over and look at it. No, you're not photographing it. You're looking at it with your eye. And honest engine, you're being honest about it, that you're actually looking at the object, but you can actually get all 110 in one night. So it actually is going to come out pretty cool the way it's working. It all just started to snowball in some emails yesterday. A little bit the day before, but mainly yesterday is when it really came together. So I think it'll probably be pretty cool. The other hot news is for those of you with RVs, apparently the fire station that is just to the south of Fort McCavitt is actually expanding, and they're cutting in a gate where you can get from the fire station to the fort either in a car or by foot without having to use the main highway. The advantage there is they're also putting in 14 RV slots with full hookups. So cheaper, it's going to be 40 a night, cheaper than a KOA, but a little bit more than a state park. But that's better than nothing out there. So that actually, they do a lot of historical recreations out there at the fort. So I figured enough of these people bellyache that they say, I want to bring my RV, and they work with the fire station. For the longest time, the fire station had a dump station for those of us that took RVs to the fort. So this is kind of cool that they're opening that up. I've asked them for an aerial pictures that I can show, so I can maybe hopefully show that at the next meeting or when that project gets done. But that's pretty much it, unless anybody's got any questions. Most of the people in this room are old enough to get this, so I'm going to leave that one there.
All right. Okay. Also, David mentioned Okie-Tex. I think the registration for Okie-Tex is due by the end of August. I think there's several of us going to that. So, all right. Next meeting is August 8th, right here. Charles Phillips is going to bring us tracking satellites, why and how. You may remember Charles gave us a presentation on this a few years ago. He's coming back to follow up. All right, next, door prizes. All right, look at your door prize ticket. See if you are a lucky winner. Oh, does everybody have a door prize ticket? Somebody say no? You said no?
Yeah.
Ay, ay, ay. Anybody else?
Go ahead, go ahead.
No.
I don't want you to miss out on the. Very good.
Paul, did you guys get door prize tickets? You did? All right, good.
Yeah.
I'm probably gonna pull Justin's out first one. Just watch this. All right. Okay. 418. 418. Well, get yourself down here. All right. Oh, you want me to bring it to you? I'll bring it to you. Okay, I'm gonna give you some choices. You ready? You can see the choices from there. One of them is a sign that says, warning, objects in telescope are farther than they appear. It says, warning, objects in telescope are farther than they appear. Now, hold on. You got any like little kids in your life by any chance? No kids? All right, forget that. I also have a map of the moon. Hold on. Moon map. Map of the moon. Okay, hold on. Well, I got a lot of stuff. We'd be here all night. I have a flashlight. No, stay there. I got a flashlight. All right, flashlight. Can you catch it? Okay, next one. Look at your tickets. These door prizes are getting better, but you're welcome. 391. 391. You got 391 out there? It's probably the guys that are talking to each other. All right, fine. Anyway, yeah, is that you? Okay, get over here. I told you I was gonna pull Justin. Okay, Justin. Okay, Justin, I got a Jupiter map.
Okay.
I got a Saturn map. I got, STS 101 onboard crew pictures. You want to see a bunch of astronauts in their underwear? Okay, I got patents.
Yeah.
Ooh, look, that looks like something that Rodney was just talking about. Torsion beam. Look at that, Rodney.
Mhm.
You should win this one. You like that one?
Yeah.
Okay, that's how you measure the gravitational force constant. See? All right, Justin. You guys wondered how I was able to predict I was going to pull Justin? That was amazing. All right, two more and then we'll get out of here. Okay. 401. All right, come on down. Let's see. Okay, while you're coming, I'm going to tell you what you got. You got a moon map, you got a Saturn map, you got a Jupiter map, you got some shuttle crew pictures.
Take the moon map.
You want the moon map? All right. See, David, I'm telling you, one out of every four. You just count it. One out of every four. Okay. I've been telling David we give away one of his moon maps, one out of every four. I can almost get exactly right. Every four, it's a moon map. Okay, last one. 4. All right, Mark. Oh, Mark. Come here. Where's Mark's door prize? Mark. Come on, man. Okay, Mark.
Yeah.
I got some radio astronomy socks. They got little radio telescopes on them. Actually, what I would like is the warning sign. The what?
At the warning sign, I have the.
Okay, yeah.
It's surprising because Mark always likes the socks, so I thought.
And then you got enough.
I like to throw a curve at him.
You want that?
I want this, I place for him very good.
There he goes. All right. Okay. Okay. Thank you for coming. See you at Mod Pizza. Thank you. See you later. You okay? It's kind of miserable over here. Be happy, Trevor. Thanks for